Hi. So I would like to start my talk by thanking the organizer inviting me here. It's very nice city and the conference too. So, Kerr parametric oscillator-based qubit. This topic, I have been working in regular qubit for ages, for 25 years. And the past 4 years, I started to do something new. And many in this community, in superconducting qubit, we start to seek some new possibility. And this is one story that I will tell you today. And okay, so here I would say there are two paradigms in superconducting qubit. One is this discrete variable dV paradigm. This is just two qubit. You know, you have two quantum level, and then you do it. You know, two-level system, and you have block sphere. And another one is just you have a harmonic oscillator, and you can populate your photons, many photons, and then you have different occupation probability. And if you can do it, if you can control them nicely, you can make like a cat qubit. Cat qubit is just superposition of two coherent states, and they interfere. But this is hard to control. And so over here, this discrete variable is easy to control, but over here, this harmonic oscillator-like system is very difficult to control. However, to do error correction, this regular qubit requires a huge overhead. However, in this distributed system, you have quantum information is distributed in many, many levels, and for the result, it turned out to be easier to do error correction. We also have some paper about this, and we are working on this error correction right now. But before that, so what we try to do is to combine these two disciplines. This is to make this harmonic oscillator easy to control. So it's a hybridization of dV and CV. So I'll tell you how we do this. So this is, oops, what happened? Okay, I don't know. Okay, it's all connected. No, oh, that. It's showing.
Let me ask if they have a good signal there or not.
Yeah, it's showing here. Well,
flickering?
yeah, it's. I don't know.
Let me ask if they have another adapter.
Oh, that. Well, okay. So, all right. So this is the. Oops. So, all right. Let's wait for this. So it is a harmonic oscillator with very weak non-harmonicity, and we can control this.
I think it's the adapter.
Yeah,
So
okay. Yeah, okay. No oscillation. Okay, so oh, I'm not so sure.
Okay, then it's not the actor. Something else.
Well, let me continue, perhaps. The pointer is not showing. Something is wrong. My pointer is not working, so maybe I'll just use. Okay, so this is harmonic oscillator, and this is nonlinearity, and then you pump this with 2 photons, and what will happen? So time, this is you. In time, you put 2 photon pump, and to a certain level, and if you do that, sorry. The potential, this is phase space. This is crazy. So you have a double well potential at, after the pumping, you have two coherent states, and then they start to tunnel through this barrier, and they have this interference pattern in tomography, and this signifies, this is cat states. And distribution looks like a bit like this. And this scheme is pretty simple. You just pump it. And this is first proposed by Goto from Toshiba. And in this paper, he also trying to propose using this system to do quantum annealing. And also, not only annealing, you can make gates and many possibilities to do this. And this is what we try to do. And so what is this cat states? Or even cat. Oops. So they are based on the even Fock-states. And odd cat is this odd Fock-states. Because of the interference, they knock out these in here. The odd one is gone, and then you see this interference pattern in tomography, Wigner tomography. And see this color is changed, reversed. And this is the experiment we want to do. Just prepare a Fock-states, any Fock-states, and then do this pumping, and you make cat states. And so this is our circuit. And we have, this is KPO, called parametric oscillator is KPO. And this is, so it's just harmonic oscillator, LC circuit. A C is just capacitor, and L is Josephson junction array. And I'll have a picture here. And so this is just capacitor, and we have this is array of DC squid, and so we can control the K. The nonlinearity can be adjusted here, and we have a readout transmon, and then we have this regular readout resonator and Purcell filter. And this is 2 photon pumping, pumping on this Josephson junction array, and then this is 1 photon pump to do the gate operation. So this is experiment. We do tomography, and this is a Fock-state, and you can make many different Fock-states. And this is initial, and do adiabatic pumping, and then you have counter diabatic pumping. This is make it faster, and it works. And So in the beginning, you have this simple occupation, but by pumping, you're pumping a lot of photon into the system, and this photon occupies in the with typical occupation probability, and at the end of the day, you get final states. These are cat states. This is, I cannot really read. This is plus alpha, this, and plus cat, minus I cat or something. I cannot really read from here. But, and we compare this with ideal state, and then we can determine the fidelity. This is the pumping scheme, so KPO pump here. So this is, and then you do detection, do the readout. And even though tomography is a little bit more complicated, but we can do it by putting pulse. Also, meaning you do the displacement and then in the different places, and then keep the scan the whole space and do the tomography. And okay, so I'll skip. So Wigner tomography, it's tedious, but you can be done. And after that, after tomography, you get amplitude, but you have to transfer the amplitude into this matrix element, and this is also very tedious, but it can be done. Yeah. It's some scheme. It's called C-gun, QST C-gun, and the bottom here. Oops. Here. So this is experiment, and then you do this is simulation, and after this you get the matrix element, and after you get that matrix element, you can compare. And this is simulation. This is target, and so both of them are target. And you have the even cat and odd cat, and see this is experiment, and they look quite similar. But you can get the number of the fidelity out of it. And after that comparison, we have you're not supposed to get this odd component, but we do have some odd component. And this is due to we are losing photons, and losing photons that, you get opposite number of the parity. And so the main main source of the error is losing photons. And okay, relaxation, it's like the coherence is not so long. If the regular transmon, we get like 14 microsecond lifetime, but making that into KPO configuration, the lifetime is a lot shorter. We are not so sure. The main, I will emphasize. The main major relaxation channel, because you have odd component. So single photon loss is the major one. And also we have a problem with thermal occupation. Our experiment was not very well protected from the thermal excitation. We have to improve that. And this is X-gate. We can do X-gate Rabi, and we can also do Z-gate. And okay, so we do process tomography to see the accuracy of the whole gate. So the final fidelity of this X and Z gate, it's about 0.8. Not perfect, as I said. We have we are losing photons in the process. That's the major reason. And later on, we do try to make entanglement. So there are many, two different ways to do that. The first one is just you prepare entangled Fock-states. We have two KPO side by side, and they're coupled. And you do this coupling, and then you can make Bill Fock-states, and then you pump on this Bill Fock-states. You get entangled cat states. As you can see, if you this interference fringe signifies you do have entanglement here. And with this, we do the tomography, and you can estimate the fidelity. The fidelity is like 0.6, because 1 qubit is 0.8, and 2 qubit is roughly 6, and this is reasonable. Again, the main source of decoherence is loss, photon loss, and the thermal excitation. And we should make much better if you can stop that. And I-swap gate, we can make that. I-swap gate, it's pretty fast, 250 nanosecond I-swap. This is much faster than other bosonic qubit, superconducting bosonic qubit, mainly because the scheme is quite simple. You just add I-swap pulse somewhere. It's like a three-wave mixing, and the scheme is quite simple. And so we can also make all sorts of different Bill cat states. You just prepare different Fock-states and then pump on it. Okay. Now, for the rest of the time, how much time I have? 2 minutes. 12. Oh, okay. Good. So we'll try to do error correction, and this is called autonomous error correction. Besides 2-photon pumping, we do 4-photon pumping on this KPO. And this is, it's not an experiment yet. This is simulation. And so we have this, this is Fock number, and then you have this because of the four photons, you have different mod states, and you choose, I cannot really see. You choose 1 mod and 3 mod states as the code space. And if you lose photon, they go to 2 mod and 4 mod states. And between this, there's a gap. This is, by analysis, you see the gap. So if you choose this, what happened is these are, so this 2 is 1 and 0 as the code space, and you can exchange this by 1 photon signal. And if you lose photon, you go to error space. But this can be saved by 1 single tone microwave. And this microwave will bring this lost photon back. So if you lose photon and back to this state, you can pump it up. This is the scheme. And if you're doing that, this is simulation. you put in some number, reasonable number of T1, T2 time. Bit flip can be increased by 1 order magnitude, and phase slip, it's improved by a factor of 6. So it's not bad. It doesn't fix 100%, but still, you can break the break-even point can be passed easily without any measurement. This is without measurement. You just keep pumping it. It's autonomous. And that will be interesting. So we are trying to do this for a while. And so somehow we haven't seen this, but I'll tell you that we see this 3-photon pumping instead of 4-photon pumping. So 4-photon is very higher order states. And we try to add a lot of microwave power, but somehow we don't see it yet. But we see a very strong 3-photon pump condition. I'll show you. This is also very interesting. So this is weak pumping of 3-photon states and strong pumping. You start to see this Rabi, 3-photon Rabi. This is simulation and measurement. And also this is measurement simulation. And so the system follow correctly. You can compare it to the simulation. And so the difference is that you start to have some higher order transition here. And we can analyze that as, so with strong pumping, you pump up to this 9 states that it's, so this guy, it's 0, 9 transitions here. And this state is 0, 6 transition. And here is 0, 3 transition. This is the main one. So the system, the experiment is following the simulation nicely. And okay, 3-photon pumped state, we do the tomography too. And it shows this triangular structures and we're changing some condition here that it follows quite well. And these colors, so this is mod 0, mod 1, mod 2 states. And so this represent these 3 states. And we can also, okay, so we're changing the displacement. And this is measurement. And this is reconstructed. And with, we have to correct the car rotation. You rotate it back. And this is simulation. So simulation and this reconstructed tomography looks very close. So I would say we're doing something right. And 3-photon, this is a new result, and we are not so sure what we can use for this, but we see a gap there. So maybe this is a well-protected, maybe we can use this as a resource somehow. But anyway, we are trying to do 4 photons to improve, to demonstrate some error correction, autonomous error corrections. That's the one direction we are working on. Okay, this is already the conclusion page. So we did KPO without many group using a 3D cavity to do this. And our experiment is just all planar. things, and we don't even have cavity. We just have LC resonator, and we can demonstrate it that dV converted to the CV, cat states, Fock-states to cat states. So this is entanglement-preserving conversion, and this is quite interesting. I think we can go back and forth. Universal gate, XZ and I swap was demonstrated. So our fidelity is not so good yet. We have to improve that. But anyway, with all these properties, KPO can be a scalable quantum information processing platform. I mean, superconducting KPO. So this is one claim. And we are working toward the autonomous quantum error correction with full photon pumping. And so meanwhile, the 3-photon pumping is working and showing some reasonable result. And thank you very much for your attention.
Okay, thanks a lot. Any question? There's a question, Matthias.
There's a possible point. Yeah, thank you. You showed on the slide with the, or on one of the slides with the 3-photon pump, one plot of the, I believe it was Rabi oscillations for weak pumping and one for strong pumping.
Yeah.
I'm not quite familiar with this distinction. Can you elaborate maybe what's the difference between these two pumping regimes?
So you just put more power into it, so you excite to the higher state.
Okay, and that then manifests in this extra blue stripe that you saw on the plot?
Oh, here.
Yeah, that one.
This stripe?
For example, also
Yeah.
the
So this
triangular
is
one, yeah?
due to this higher order transition. So this guy, I designate this diamond. Diamond means here. So this oscillation, I mean, these states appeared because of this. With larger power, you excite the 0-9 transition, and that appears here. And we can check that with simulation.
All right. Okay, I think I understand. Thank you.
Yeah.
Okay. I think the next question should be somebody over there. Okay.
Thank you for the nice talk. So in the lines of the previous question, does it mean that when you're going to achieve this 4-photon pumping, you're at the same time doing the 3-photon and the 2-photon pumping? I mean, is that a problem?
No. Just do 4-photon pumping. And then to do logic, you just do this 1-photon signal that can the switch from 0 to 1.
But then the unharmonicity is enough to guarantee that you're only going to be driving this 4-photon and not weakly the 3-photon.
Yeah, well, no, it's okay because the cat state is you can populate all these things and automatically you occupied higher state. This is all included in the scheme. So doing 4-photon, you have to occupy many higher states.
And the reason you have not achieved 4-photon yet?
Yeah, so I'm not so sure. We are kind of puzzled. We don't see any signal yet. That's kind of puzzling. I'm scratching my head. hopefully we will start something, see some signal, and we can twist some knob, try to enhance that stronger. But we haven't seen that yet.
Thank you.
More questions? We have time for more questions.
So you said that one of the main loss mechanisms is the single photon loss, and by reducing that, you could increase the fidelity of ISWAP from 67 to 97. What is the optimization that you have to do to achieve that?
Losing photon, I'm not so sure what we have to fix, but we know it's losing photon is bad. The Q of like a transmon has higher non-homogeneity, but the lifetime is a lot longer, and you don't. But here, somehow, our T1 is much shorter, and this I'm not so sure. Maybe we have to try many other things. And that is related to photon lifetime. Yeah, this is just, we're just starting this a while ago, and many things is not optimized.
More questions?
So maybe you mentioned it, but I didn't get it. What is the difference between what you have shown and the work done at Yale?
It's similar, but they use, there's a subtle difference. Okay, they have a 3D cavity, and cat state is, they also use transmon as the source, and then you create cat state in the 3D cavity. So because of 3D cavity, their lifetime is longer, but here this is just two planar, and we don't do. We just use this Goto scheme. You just do two photon pumping, and then you get cat states automatically. Not complicated. Yale is much more complicated. I like the scheme because it's very simple. And other technical problem, it's not problem. We showed everything in tomography. They saw this Rabi flip first. And it doesn't have phase information. If you do Wigner tomography, you know everything about phase and amplitude. All the information is here. But basically, it's a similar things. The largest difference, I would say, it's the 3D and 2D system.
Thank you.
Okay, any more questions? I have a short question. You move the Fock-state into the cat state. Can you use this as a quantum memory?
Well, it is memory. I mean, it memorizes in different shape. I mean, different number of the photons. Yeah, as long as the states stay here. The memory time is not that long.
Okay, yeah. But you can correct it, so it's a kind of a...
Oh, yeah. If I can correct it, yes, that will be good. Yes.
Okay.
Yeah, if you can do error correction without reading, that will be interesting.
Okay. No more questions? Okay, let's thank again the speaker.